coming. I'm Douglas Blackstone. I'm the director of ODYSSEY, and it gives me great pleasure to introduce William Hughes. Bill is retired from 37 years with NASA.
That's correct.
And I think he's mainly what he's doing today is still working on NASA projects for the Applied Science Lab here at HOPKINS, Applied Physics Lab, sorry,
Right.
the APL. And we've had several instructors from the APL, and they've all been very good professors and good lectures, and so I look forward to Bill Hughes being one of those. Let's give him a hand. Thanks.
Thank you for the introduction. I'm pretty well known as a loud talker, so I hope that you can hear me. If you can't hear me, make a funny face. I don't see any funny faces. That means they can't hear me. Okay, so I appreciate you coming out for this talk. It's, I spent my career working on measurements of chemical species in the atmosphere, so it's sort of near and dear to my heart in many respects. But I also think that the atmosphere is an area that is receiving more and more attention, particularly with the threat of global warming and hanging over our heads. And I would say that my goal for this course, well, I want it to be fun. I want you guys to have fun, and I want you to enjoy the course. But I want you to learn some stuff. And after I started looking at it, I decided the stuff that I want you to learn is hard. And I apologize. I had a physics teacher when I was in undergraduate school one time. He asked me how I was doing in school. I said, well, I got A's in all my courses except physics. He said, well, physics is hard. So I'm hoping we can get over that, though. But I appreciate the fact that you're going to have to make an effort. But anyhow, my goal is that at the end of this course, you will be able to have a discussion with your friends and enemies who are climate change deniers, and you explain to them why there's no way in the world that man-made climate change can't be a real thing. You can explain to it how it works, and you'll win this argument. So that's my goal for you guys in this course. And although the physics is hard, when we get to the point of the argument for why this is the case, it's not a hard argument to understand. And so hoping that that'll just be something that you'll be able to take away. And if you have other goals beyond that, let me know what they might be, and I can address them. I will also say this, that I am easily distracted. If you ask me a question, we may just spiral out of control into some long digression that's interesting to me and interesting to you, but will prevent us from ever reaching the end of the class. I'm not saying don't ask questions, I'm just warning you what can happen. And so the other piece of this is because we're having a hard subject, and we're going to have to learn some physics and some chemistry to be able to address these things. And I know that at least one of the people in this room has got a PhD in physics, but I'm assuming that that's not the case for most of you. And so at the risk of insulting people, I'm going to have some of the things that we talk about are very, very elementary. But if you haven't been working in a technical field, you may have forgotten sometime over the last 40 to 60 years, and so it might still be worth talking about. So, one more thing. Before I begin, I'm going to tell you a story. I don't know if it's a true story or not, but it's a good story. It's about Albert Einstein. Most of the stories about Albert Einstein are good stories. Probably half of them are true. But anyhow, it was a cocktail party, and his hostess or somebody came up to him and said, Dr. Einstein, would it be possible for you to take a few moments to explain the theory of relativity to us? And he said, well, yeah, I can give that a shot, but before I do that, let me tell you a story. He said, a friend of mine and his friend, who was blind, were walking down the street, and he said to his blind friend, I want to go in this cafe and get a glass of milk. And his friend said, oh, said, I'm not familiar with milk. What's milk? And the guy said, well, milk is white liquid. He said, well, I understand liquid, but white? What's white? I said, well, white is the color of a swan's feathers. He said, well, I know feathers, but what's a swan? He said, well, a swan is a bird with a crooked neck. He said, well, I get the neck, but what's crooked? And he took the guy's hand and he held it like that. He said, that's straight. Then he bent it like that and said, that's crooked. And the guy said, okay, so that's what milk is. Okay, so we have a problem like that a little bit in talking about some of this stuff. Physicists have a vocabulary, words that you use all the time, in a general sense, have a more specific meaning for a physicist. Words like temperature and energy. So I'm going to try to sharpen up the definitions for those words, and I'm going to try to bring you along through a little bit of science, try to teach you a little science, a little chemistry, a little physics, and hopefully we'll be able to tell a story and have some fun at the same time. So here's the program, the 4 lectures. The first lecture is going to be the background and a little bit of talk about just what the structure of the atmosphere is like, what the atmosphere kind of looks like. The second one is going to concentrate a little bit on chemistry. I know air pollution is a very complicated subject, so I'm going to touch that very cursory look at air pollution. Ozone layer, I worked on the ozone layer when I first went to work for NASA, so I know a lot about that, so I will probably talk more about the ozone layers because I'm more comfortable in that area. Then the third lecture is going to be about atmospheric physics, what determines the temperature of the Earth, and what can we do or what are we doing to alter the temperature of the Earth. And the last one is just going to be the pretty picture talk. I'm going to talk about some instruments that have been used over the past couple of decades to make measurements in space, and a little bit about how they work, but also some pictures of the instruments and some pictures from space. And I'm going to show you a couple of movies and things like that, so hopefully we can end on something that's a little lighter and maybe just more fun. But anyhow, so that's the program. Okay, so at the very, very beginning, actually, why don't you read the first half of this slide and tell me if this is something you're so familiar with. If there's anybody that doesn't know how to do scientific notation and arithmetic, raise your hand and we'll go through this slide. Otherwise, we're going to assume everybody's comfortable if I say 10 to the minus 23 is a really small number and 10 to the 86 is a really big number, and you know how to multiply. Everybody comfortable with that stuff? Okay, good. We don't have to do that. As I say, I didn't know where the audience was going to be coming from. I know that the man on the street doesn't usually use exponents to talk about numbers. Okay, so here's another little piece of, oh man, this is good. Woo! Somebody wants me to contribute to their political cause. Can't imagine. Okay, the exponential function. Exponential function comes up a lot of times. Most of you probably run into this too, but I'm going to explain it like this. This is any time that you have some kind of a phenomenon where something is changing. It might change with time, it may change with distance, but something is changing. But the size of the change is proportional to how much stuff you've got at the beginning. So like money is a perfect example. If you're earning money at 10%, you got $1,000. At the end of the year, you got, $1,100. If you got $2,000, you get $200 at the end of the year. So the size of the change depends on what you start with. When you have an equation like that, that lends itself to the exponential function. So here's an example right now. Suppose you have N dollars in a savings account, pays you 100% a year. That's a good savings account. At the end of the year, you'll get your interest. You get 100% of the interest. So your total holdings, here I am right here now. So you get 2 times N at the end of the year. But suppose instead of it just paying you the compounded interest annually, the compounded semi-annually. So at the end of the first 6 months, you got half of it, and then the second half of the year, you get another that. So at the end of the year now, instead of having 100%, you've got 125% gain. So compounding speeds up the rate of growth. Okay, well, suppose you compounded it every month. Then you have n times 1 plus 1/12, which is 1/12 of the 100%, times 12. That turns out to be 2.61 times. Okay, suppose they just did it all the time. Suppose you just did it, as I say, a jillion times. At the end of a year, you would have 2.7182818 times however many dollars you have. Some of you may recognize that number, 2.718281828. That's the number E in math. E stands for exponential. And that's where E comes from. E turns out to be the value of an integral of a function. And so, the important thing is just the bottom line is that for continuously compounding pain, and that's the way most physical processes are just going on continuously, at the end of time, the change is going to, what you have at the end is going to be E to the rate times the time. Okay? In this case, rate is 1, time is 1 year, so that's 1, so n times E to the 1 is E, so n times 2.7182818 $. Okay, but that's going to come up a few other times in more than one context. Alrighty then. So here's what the exponential function looks like plotted. And so if you start out at 1 and the exponent is positive, that means you get exponential growth. And so it takes off. So there's lots of things we talk about being exponential growth. The growth of microbes in a petri dish and things like that. It's exponential for a while until food runs out. Then it slows down again. It's the same thing with the population of the earth, I guess. But anyhow, the right-hand side is exponential growth. The left-hand side is what happens when the exponent is negative. You start out at 1, and as the exponent gets bigger and bigger and bigger, the amount you have is to be less and less and less and less and less. This would be something like radioactive decay. Suppose you had a big piece of plutonium sitting on your desk. So they talk about, for radioactive decay, sometimes the half-life. Instead of using the E time, they use the time for it to go down by 2. But the point is, it's the same kind of a deal. You can use any number in that exponent if you want to. You can fit these curves with any shape. But the point of the matter is that after the first billion years, you got half as much plutonium. Okay? After the next billion years, you haven't lost the rest of it because the rate at which you're losing is proportional to how much you got. You got half as much, so the rate's half as much. So you lose another half. And you lose another half and another half and another half. So that's the way exponential decay works. Okay? Questions? Comfortable? Most of you have seen this before, I presume? Yes, sir.
That can never reach 0.
It doesn't. In practical terms, of course, it does because, I don't know, if you count dollars at some point when you get down to really small amounts. Okay. All right, now, okay, so that wasn't too bad. That was the preliminaries. Now we're going to actually talk about science, physics a little bit. We're going to talk about the ideal gas law. Now, the adjective ideal does not apply to the word law. It applies to the word gas. This is the behavior of an ideal gas. And there are good examples in the real world of ideal gas. Ideal gases are gases where all the molecules just act like little billiard balls. They bounce around off of each other and they don't interact very much. And so it's just ping pong balls running around in a box. That's pretty much a model of an ideal gas. Gases that are chemically active, for example, say chlorine gas. Chlorine gas reacts with itself, among other things. So gases that have electrons sticking out of them and are reactive, they have a tendency to stick to one another. And so they don't just bounce around like billiard balls. They cling to one another, and it kind of messes up the equation. But for an awful lot of gases, the ideal gas law is pretty effective, and it's pretty good for the atmosphere. So what does the law say? It says pressure times the volume is equal to the number of molecules in the volume times this constant, the Boltzmann constant, times the temperature. And the little graphic on the upper right sort of shows the model of the difference between high and low pressure. When you have a higher pressure, the gases are closer together and they bounce around each other. They exert more force on one another. These pictures are, this is Charles, I can't remember his name in here, and Robert Boyle. Boyle is the guy that discovered the variation of the fact that pressure and volume are related. If you double the pressure on a gas, the volume goes to half. That's Boyle's law. Charles discovered the variation of the behavior of gases with temperature. The point of that, if you look at these guys, you can tell this is old stuff. One of the things that people that are arguing about climate science say, it's not settled science, One of the arguments I'm trying to make is the science that relates to the atmosphere is very old science. It's been around for hundreds of years. This is not cutting edge. We don't really know stuff. This is well-established stuff. That's just another point you can make in your little arguments. This is old stuff. I wanted to say a little something about temperature. Temperature is a term that we all toss around, and temperature is really just kind of an arbitrary number. I mean, the Fahrenheit scale, for some reason, they said 32 is freezing and 212 is boiling, and the Celsius scale, they said 0 degrees is freezing and 100 degrees is boiling. And the truth of the matter is that you can have your own degrees. You can have a degree can be however big or however small you want. The only thing that really is fixed is that temperature is essentially a measure of how much energy is contained in something. And if it gets down to really, 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 really cold, there's no energy. And so that's the true value of 0 for temperature. And of course, that's not an attainable temperature in reality because of quantum mechanical effects, and we're not going to talk about that. But the point of the matter is that the true 0 is the absolute 0, and it's about minus 273 degrees on the Celsius scale, and it's about minus 450-something degrees on the Fahrenheit scale. We tend to use the centigrade scale, and this K over here stands for Kelvin. Lord Kelvin is an early researcher on temperature, and the Kelvin scale is the absolute temperature in Celsius degrees. And so this number, the Boltzmann constant that we've got there, is the one that's appropriate for Kelvin degrees. Do I need to say anything else about that? Yes, ma'am. Yes, sir.
Maybe this is a highlight of this difference between chemistry and physics and math. I remember this ideal gas law, but I remember it as PV equals nRT.
R is, yeah.
Is
So
that the Boltzmann constant?
no, so chemists. So this is yeah, it is kind of different. So N is the number of molecules. Then the constant is K, the Boltzmann constant. If N is the number of moles of the gas or the material, and a mole of gas is like this Avogadro's number times the molecular weight of the gas. So anyhow, so then if N has got a factor of 10 to the 23rd figured in there because you're measuring in moles instead of individual molecules, then you use R. And instead of R being this incredibly small number, R is like 22.4 or something like that, right? But
Yeah. So moles is chemistry, no wonder.
yeah.
When
Yeah, that's it. It's the same formula. It's just it's just, you know, if you're counting your molecules one at a time, then you use moles per constant. If you're counting a mole at a time, then you use the gas constant R. Okay. I'm going to let you look at, huh? Well, this is terrible stuff. You know, this is what I was talking about when I said I'm going to get a little more specific. I'm not going to toss around the word energy without having units or something like that. So what's pressure? Pressure is the force per unit area. Pounds per square inch. That pretty much says force per unit area. Also kilograms per square meter. Feet of water, inch of mercury, bars, pascals, are various used because different people working with pressure in different capacities, people like to have numbers that they can write down, you know, in a small amount of space. So you try to use your unit of measurement to make the arithmetic simple and easy. Okay. Now, force. I'm down to the second paragraph now. Force is the ability to do work or make something move. So you've heard force equals mass times acceleration is one of Newton's laws of motion. Okay, so force is a mass times acceleration. Force applied to object makes the object speed up or slow down. If it's a small thing, small mass, then the same force makes a bigger change. Mass is measured in kilograms in our units. Acceleration is meters per second. So force, which is mass times acceleration, is a kilogram meter per second squared. And 1 kilogram meter per second squared is called a Newton, named after some old guy. Now the energy is the same thing as work. And energy is a force, a Newton, acting over a distance. In other words, if I was pushing on something with a force of 1 Newton, and I did this force for 5 meters, then I would have I would have expended energy to move that thing. And so the force times the distance is the energy. So the unit of energy is the Newton meter. Newton times a meter. Newton meter is called a joule. Joule's another old guy. Sometimes the rate at which energy is delivered or applied needs to be measured. The rate at which the energy applied would be joules per second, and a joule per second is a watt. It's another one. So I hope you can remember these things. We're not going to beat them to death, but I mean, I just want you to have seen it and at least be comfortable with it. Now, there's one point that I didn't put on this slide, maybe I should have, but it is this, that pressure times volume would be, pressure is a force per area, and a volume is an area times the length. So those areas cancel out in pressure. Pressure times volume, there's an area in the top area of the body, and pressure times volume is a force times a length. It's force times a distance. So that's work. That's an energy. So the PV side of the ideal gas law is energy. And that means that on the other side of the equation, the NKT is energy. And so T is just a number. So K is, and N is how many of them you got. And so the total amount of energy stored in some object, box of gas. Suppose you have just a box of gas, it's a simple gas, so all it's just is billiard balls bouncing around. They got 3 degrees of freedom. They can go this way, they can go this way, or they can go that way. Those are independent ways to store energy. So every molecule in this gas could potentially have 3 times this 1/2 kT. So that would be, so when I say the temperature is a measure of how much energy, that's the amount of energy in that gas. Now, some more complicated gases have additional ways to store energy. In addition to having this and that and this, they also have the ability to do like that. So they can store energy in what's called the vibrational modes of the molecule. Atoms can't do that, but molecules, because they got two atoms connected, and two or more can do it. They can spin. They can spin about this axis, they can spin about this axis. So they have rotational modes. So one of the things that early guys did when they were taking gases, they would put a certain amount of heat into a gas, and they would look at how much warmer the gas got. And they found that for some gases, a certain amount, because the gas only had these three modes of motion, you get a certain amount of temperature rise for a certain amount of energy. But if you had a gas that also could store energy like this, or could store energy by spinning it around, the temperature rise wasn't as great because it was storing energy in more modes. Okay, so the heat capacity of gases, which is the thing, this is another interesting thing. All these guys are old guys. They were all old rich guys, and they were just doing this stuff for the fun of it. It's kind of amazing how wonderful it is that we had guys that had the curiosity and the means to investigate the world for us like that. They gave us a good start. There's a few people that kind of do that stuff now, but it's certainly a lot harder. The experiments cost more than this. Okay. Let's get rid of that slide. Yeah. Okay, quiz. Energy. What's that units of energy? No, I'm teasing. Yes, sir.
The last part was about calories. Did you want to mention that?
Well, I didn't want to say too much. The point of the matter is, like all of these things, different people use different units for what makes what they're doing convenient. So a calorie is a certain amount of energy. It's amount of, one measure, it's the amount of heat necessary to raise the temperature of a cubic centimeter of water 1 degree centigrade. So I mean, it's a quantifiable amount of energy. It's also the amount of energy in stored foods. With people, there's a whole group of chemists, I don't guess people do this so much anymore, that used to do chemical reactions, and they would put two chemicals inside of a thing they called a bomb calorimeter. They would measure the temperature of it, then they would initiate the chemical reaction. The chemical reaction would take place, and in that chemical reaction, energy would be generally released. That would raise the temperature of the thing. By measuring the amount of temperature, they could calculate how much energy was released in that chemical reaction. I had to do it in laboratories when I was an undergraduate. I don't know if anybody actually does that kind of stuff anymore, but they might. Okay. That answered your question anyhow? Simple enough answer? Yeah. Okay, so now, how do we measure pressure? This is another old guy, Torricelli. One of the units for measuring pressure is torr, named for Torricelli. Torricelli invented the barometer. As I say, settled science. When he did it, they weren't exactly sure what was going on. They didn't exactly know why the mercury didn't just all run out of the tube when you did that. Until they found out, though, that if they took one of these things up on top of a mountain where the air pressure was lower, the column of mercury in the tube wasn't as tall. So they kind of figured out eventually that it was related to atmospheric pressure. When Boyle discovered his law about the variation of pressure with volume, he had a tube that was shaped like a U. It was closed on one end, and he poured mercury into the thing until it became stable. Then he looked at the length of the column of gas on the left-hand side, and then he put more mercury on the other side, put more pressure on it, increased the pressure, and the column got less. In doing that, he observed that if you double the pressure on this side, you have the volume on the other side, and that's that. The PV is conserved law. So that was the way Boyle discovered his law. It was basically using a version of a barometer. There's a lot of other ways to measure pressure. This is just an evacuated cell. The pressure goes up, it squeezes the accordion air, moves the little deal. These little barometers, little round barometers that are so pretty that people have hanging on their wall, rosewood case and all that, they tend to be analog barometers. They're pretty good. Okay. Any more questions about that? So how are we doing on time? Just 30 minutes in, that's not too bad. Might finish early. And I'll go out for a beer. Okay. The atmosphere is exponential. Now, here's the reason we had to talk about interest. All right. Suppose you have a little box of air. This box of air right here. Okay. So, to keep that box of air from falling to the ground, there's a pressure on the bottom of that box of air. And there's also a pressure on the top of that box of air, but it's a little bit less because the pressure down here is this pressure up here plus the weight of the air that's in the little box. So this delta P, the increase in pressure to the top of the bottom, that delta P is basically the weight of the air in the box. So that's what it says up here. Delta P is the density times the volume of the box times mg is the weight of one molecule of air. Now, air is not all the same molecule. It's mostly nitrogen with some oxygen. Nitrogen weighs 28, oxygen weighs 32. It turns out the average weight of air is about 29. So 29 is a good number for m. G is the acceleration of gravity. So mass times an acceleration, so that's a force per area. This is just a number per volume. This is times the volume, so that's just a number. So the change in pressure is going to be a force per area. So the units of volume. Okay. So using the ideal gas law in this formula, take NV, and that's you solve ideal gas law for NV, and you get P over KT. So now we got delta P is P over KT times the volume of the box divided by the area. I took this area right here and I moved it over here times mg. So okay, so the volume of the box divided by the area, that's this area down here times the height of the box, which is z. So this term right here, v box over a becomes z, the height of the box. So we now got delta P is the pressure times mgz over kt. Okay, well that's another one of those formulas where the change is proportional to the amount of stuff we got, to the pressure. So this means the solution to this equation is going to be an exponential. And the rate coefficient is going to be mg over kt, and the thing is variable is z. So as you go higher and higher in the atmosphere, the pressure decreases. Okay? So this is on the decreasing side of the exponential function. And so here it is written out in all its glory, the exponential function again. And in this case, if you multiply mg over kt, it turns out to be about 7 kilometers. So that basically is saying if you start up and up and up and up, by the time you get to be at about 7 kilometers altitude, then this exponent becomes 1, and so you are down by e. So the atmosphere has gone down by a factor of 2.8 by the time you go to 7 kilometers. By the time you go to 14 kilometers, it's down by 2.8 squared. And so that's the way, that is the exponential fall off of the atmosphere.
You say, you mean the density of the atmosphere?
Well, the density and the pressure, they kind of scale together.
Okay.
Yeah. The PV equals mkt formula over V, so P equals N over V, which is density times KT. K doesn't change. T doesn't change too much, and so it kind of says, ideal gas law kind of says the pressure and the density kind of go along together. Not exactly. Now, I told you a big lie in this whole thing. Does anybody know what the big lie is? Okay, good.
Ideal gas?
Huh?
Ideal gas? It depends on
It's not that as much as this. This calculation assumed that T didn't change. We just said T was a constant. I just told you over here, fold T into that formula, the answer is 7. But atmosphere is not the same temperature all the way up. So the truth of the matter is, it's not purely an exponential, but it's close. The temperature changes between, temperature changes in the atmosphere in a Kelvin scale go from around 300 at the surface to 250. So it changes by about 15% or something. So in the grand scheme of things, it's pretty constant. Depends on what you're trying to do. Yeah.
Does the ratio of the various components of air change? The ratio of nitrogen.
It doesn't very much in the lower atmosphere because there's just so much boom, 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 bouncing around and stuff like that. As you get higher and higher and higher in the atmosphere, and the number of collisions get less and less, the atmosphere begins to fractionate. The heavier gases fall off faster. They got a bigger M in this formula. They fall off faster than the lighter gases. So the lighter gases become more prevalent. But you don't see that so much in the lower atmosphere. It's a good question. Yeah.
What's lower versus higher? What kind of scale?
100 kilometers is high. Yeah.
I was taught adiabatic rate every 1,000 feet temperature drops. So you have to
Yeah, something like that. Now you're talking like a damn meteorologist, though. But that's right. I mean, that's generally true. I'm going to talk about that in just a second.
Okay.
A little bit. I'm not going to use the word adiabatic.
understand.
Okay.
The,
People comfortable with this derivation, though? Yeah.
your 6 times 23, you're saying that 6 times 23 of those air molecules,
Yeah.
its mass would be 29 grams?
Yeah, about that.
If you had,
Because the atomic 6 times 10 to the 23 is Avogadro's number.
okay, so that's that.
And so the molecular weight of the average molecular weight of air is about 29. It's sort of a balance between the nitrogen at 28 and the oxygen at 32. Okay? Okay. Get a little more real. I just told you about the lie. So here are some more representative numbers on what the shape really looks like. This kind of answers your question. You see the pressure and the density kind of track along pretty much. They do pretty much the same thing. These peaks, those have to do with places where the temperature changes. I didn't know there was a standard atmosphere until I went to work for NASA. Some friends of mine helped write the book, so they gave me a free copy of it, and I still have it. I don't think the standard atmosphere has been changed since 1976, but it was probably pretty close to right at the time. It's got a lot of information in there. But here is the temperature variation going all the way up to about the 100 kilometer altitude I was talking about. So here's the thing, you're adiabatic 3.5 degrees per 1,000 feet. Well, that holds up to about 11 kilometers or so, like that, 10 or 11 kilometers, then all of a sudden the atmosphere stops cooling off, and in fact actually kind of warms up. This thing right here is just It's just something that the book said. This is what we would use for, if you were trying to approximate the temperature of the atmosphere at various altitudes. But anyhow, so temperature turns around, increases for a while, gets up to about 50 kilometers, it turns back around and starts cooling off again. Anybody know what the reason for the temperature increase is?
Ionization.
No?
Greenhouse gas.
It's the ozone layer. That's the stratosphere. The stratosphere is produced by the ozone layer. There's a whole bunch of ozone at that altitude, and ozone absorbs ultraviolet light from the sun, which the upper atmosphere doesn't absorb. So at some point, all of a sudden, there's a new heating term in the atmosphere. The air itself is absorbing energy from the sun, and that causes warming. And so the ozone layer basically starts somewhere in here, depending on where you're on the Earth. It goes up about 50 kilometers. It's that, the absorption of that light is important to us because that ultraviolet can kill us. So we like having it there. But at the same time, it also changes the whole temperature profile of the atmosphere. And that has some interesting effects. I can't think of anything else to say about that right now, but if I do, I might come back. Okay, so another fair question is, what's the atmosphere made out of? Okay, you see it's mostly nitrogen. Most of the rest of it is oxygen. Almost 1% of it is argon, which nobody ever even thinks about. Thanks, Doug, to see it. And then there's all this other stuff that's trace gases, and then this box over here shows what was once upon a time the mixture of the trace gases. And I'll tell you that the red chart over there is just totally wrong. I mean, all of those things have changed substantially over the last, I don't know how long that chart is, a couple of decades. Lots more carbon dioxide in the atmosphere, more methane. Helium and neon are about the same. Ozone, up and down. And water, of course, is very variable. Water goes from anywhere from about 0.5% or less. You get out in the desert, it's less than 0.5%. You get in the tropics and the jungle, it might be up as high as 2%. So water vapor is kind of all over the place. But anyhow, that's kind of now, as far as when we talk about these trace gases, and that's the part that's kind of interesting because other things do the thing. We use a unit to talk about. We use a unit to talk about which are parts per million, or parts per billion, or even parts per trillion. So like carbon dioxide right now is running at about 400 parts per million. So that means if you grabbed 1 million molecules of the atmosphere and sorted them out, about 400 of them would be carbon dioxide. And that's the number that's been going up for the last 150 years. Some of the other gases, though, are even rarer. They're at the parts per billion level, so you have to take a billion. And some of the gases, it still has significance for us. You have to take 1 trillion molecules to get a few hundred of the one you dissipate.
Is the percentage of trace gases change as the amount of carbon dioxide goes up?
Oh, yeah, a little bit, but I mean, it's still, you see how the trace is still only 1/10%. So so 400 parts per million, we'd have to have, 25 times more carbon dioxide to get to the 1% level. We'll never get there. But I mean, that's just, okay, this is just a fun calculation. Maybe it's fun. It's numbers. How big is the atmosphere? Okay, if you put in typical values for the temperature and pressure at the Earth's surface, you can use hydrogen gas law. You can solve for N over V, the number of molecules per volume, density. And it turns out to be about 2.5 times 10 to the 25 molecules per cubic meter. So I told you there were going to be some big and small numbers. That's a big number. Okay. All right, and I already told you that the pressure is exponential with a scale height of 7 kilometers. Now, one thing that means is that you took the whole atmosphere, the column, all the way up to the top, and you mashed it down flat so that instead of having this exponentially decreasing, it was constant. That would be a layer 7 kilometers thick. It's the integral of the exponential function. The point matter is, so that's basically saying, on average, the atmosphere is 7 kilometers thick. If it were all at normal surface pressure. So, okay, so now, if the atmosphere is 7 kilometers thick, it's this shell all around the Earth, 7 kilometers thick. We want to calculate the volume of that shell. Okay, well that would be 7 kilometers times the area of the Earth. Is that sensible? That makes sense? That's how you would do it. So what's the surface area of the Earth? Does anybody remember what the formula for the area of a sphere is? I do. Yeah, 4 pi r squared. So this is easy to remember. Not that you need to remember it, but because think about a baseball. A baseball has kind of got 2 circles like this, and 2 circles like that, and that covers up the whole outside of the baseball. And each one of those circles is about the same as the pi r squared cross-sectional area of the sphere. So basically the area around the whole sphere is 4 pi r squared. So now you can remember that forever. Or not. All right, but anyhow, so you take the radius of the Earth times 4 pi r squared, you get the surface area of the Earth, 5 times 10 to the 14th square meters. And then you multiply that by 7,000 meters, which is the thickness of our shell. And so then you get the volume of the atmosphere is 35 times 10 to the 17 cubic meters. Okay, and we already know from the top that every cubic meter is 2.5 times 10 to the 25. So you multiply that by that, and you get 88 times 10 to the 42. So let's just say there are 10 to the 44 molecules in the Earth's atmosphere. Seems like a lot.
Sorry, the volume was, could you just go back to what the volume was for a second?
Yeah. Is this fun? Is this interesting at all? I mean, okay.
The last line, how do you go from 88 times 10 to the 42nd to rounding to 10 to the...
Well, I just said 88 is pretty close to 100.
Yeah.
So 100 would be 10 to the 2 times 10 to the 42, 10 to the 44.
Oh, okay.
Okay? Yeah, so I'm playing fast and loose with the numbers. Just think of it as the federal budget, right? You know? A billion here, a billion here. You know? Okay. Pretty picture. One thing NASA can do is make pretty pictures, I'll tell you that. Okay, let's say in a typical breath of air, you get about a liter. You actually get probably more than that, but a liter is only about a quart. But let's just say it's a quart. So that's 10 to the minus 3 cubic meters. So in your whole life, 20 breaths per minute times 60 minutes times 24 hours times 365 days times 30 years. Lifetime, a person breathes in about 31,500 cubic meters of atmosphere. We multiply by our 2.5 times 10 to the 25. So we get that in the 30-year lifetime, you get about 10 to the 30th molecules of the Earth's atmosphere. So the Earth's atmosphere was 10 to the 44. So in your whole life, you're not going to breathe the whole atmosphere. But you're going to get about 1 over 10 to the 14th of it. Okay? All right, so let's just say Jesus lived about 30 years, or Hitler lived about 30 years. So that's about how much they basically in their lifetime inhale about 1 over 10 to the 14th of the atmosphere. But every time you take a breath, you breathe in 10 to the 22 molecules. 1 out of every 10 to the 14 of those was in the lungs of Jesus or Hitler at one time. So that means every breath you take, you're sharing air with Jesus and with Hitler. Now, I'm not actually sure that the atmosphere mixes well enough for Hitler to really be in there, but I'm pretty sure it mixes fast enough for Jesus. It probably mixes fast enough for Hitler too. But it's just kind of an interesting anecdote, shall we say.
One question.
Yes, sir.
What percentage of the air do you actually consume with breathing?
We need to consume.
Actually utilize? How much of the oxygen is actually absorbed?
Well, I don't know. I think that depends on how healthy you are. To some extent. You don't necessarily put it all back out. It all comes back out eventually. Besides that, over a lifetime, you die and rot, right? Yes.
The terms that are up there, how did they come up with that wordage for this term?
Yeah, I'm going to talk about that in practically the next slide. Okay. So to be perfectly honest, I don't remember what tropo means. Now, it's the part we all live in. But here's the thing about the troposphere. The troposphere is the part of the atmosphere where the temperature is falling off. And I'm going to talk about this in a minute. Maybe a little ahead of myself. But the point of the matter is, let me go to the next slide and come back, just because I think. Let me see if I got maybe I'm a little confused about it. Yeah, well, we're going to talk again. I'll go back again. Anyhow. In the troposphere, if you have some warm air and it gets pushed up, the air around it is colder than it was before. And so that dense air pushes it up more. And so now the air is even colder. And so the temperature falling off means warm air gets pushed up and up and up and up. So when warm air starts moving up, it moves up and up and up and up and up. When you get to the stratosphere, all of a sudden, the driver for that warm air moving up stops because the atmosphere starts to get warm again. So now the warm air is going up into air that's warmer than it is, so it stops going. That is why cumulus clouds look like that. They're driven by convection. They keep going up and up and up and up and up until they hit the stratosphere and then boom. There's no force to keep the air going up, and so they stop. So the thing about the stratosphere is, if you take a parcel of air in the troposphere and you displace it a little bit, it's now at a different temperature from its surroundings, and the force tends to drive it up, so it tends to keep going. If you're in the stratosphere and you displace a little bit of air, it's heavier than the air around it, so the forces tend to push it back down. So up and down motion of air in the stratosphere doesn't happen. So the stratosphere tends to be layers, strata. The atmosphere is stratified, and that's why they call it the stratosphere. Okay? Mesosphere meso means middle. There's nothing interesting going on there. For a lot of years at NASA, they called the mesosphere the ignorosphere, because nobody much investigated it. When you get on higher up above the mesosphere, that's when all of a sudden the sun's UV is blasting molecules apart. You've got ions, you've got a whole different kind of stuff going on. You've got electric fields moving things around. And I'm not going to talk about any of that stuff either, but it's a whole another ballgame. But interesting for those who do this.
So you're going to talk about not losing clouds? Come on your graphic there.
Yeah. I can say a little bit about them. Yeah, I can say. They mostly occur in polar regions. And at the pole, the stratosphere gets down real low. And there's a lot of transport into the polar regions coming from below. The general circulation moves air away from the equator too. So you actually get air coming down. So you get air that has moisture in it that's not coming up from below, but it's coming in from the sides and down. So you can get moisture into the higher levels. And so you can't get these really high clouds because there's a different method for the moisture to get there. And they tend to be very high. You can see them from a long way away. I've seen a few. Of course, in the summertime in the polar regions, the sun never really sets, so they're illuminated, all night long. So they're really kind of neat things. So they tend to look kind of pearly, kind of like the inside of an oyster. That kind of I'm not sure what about causes that. It has something to do with the optical properties of the cloud itself. Yes, sir.
In the temperature graph on the right, I can understand in the lowest layer, the troposphere,
Yeah.
get an idea that the higher up you go, it gets colder. And then when we reach the stratosphere, you said because of the ozone layer,
Yeah.
so it's warmer. Why does it go the other way in the mesosphere? Or is that the reason it's ignored?
Well, no, the thing about it is that above that altitude, above about 50 kilometers, there's no ozone. Ozone is only sort of formed in that layer between maybe about 10 to 20 and 50 kilometers. So now there's no heat, there's no absorption in the atmosphere of those wavelength regions, those wavelengths. So there's no heating in that part. And so it's just different. There's different chemistry in the atmosphere. I'll tell you, I'm going to talk a little bit more about why ozone is there, what forms ozone, what causes it to go away. The point of that is just the ozone is formed below 50 kilometers and above 20 kilometers. And so since that's where the ozone is, that's where the absorption occurs, that's where the heating occurs. Okay?
And then for the thermosphere, the gases that...
When you get up there, it's just completely different stuff. It's now ions. It's ions and the Earth's magnetic field and solar wind. Okay, unfortunately, during the course of the lecture, the camera battery failed, and so the recording stopped on this slide. I'm just going to go through the rest of the slides and say a few words about them so that this movie will include all of the material that was meant to be in the first lecture. It will, of course, will not have any of the questions or comments or remarks by the audience, and it probably will not have any of the spontaneous attempts at humor that I may have interjected into the proceedings. We were talking about the layers of the atmosphere on this slide. Just explained that the stratosphere exists because of heating due to the ozone layer there, absorbing energy from the sun and providing direct heating into the atmosphere between about 20 and about 50 kilometers. And we're going to move on to the next slide. So this slide is talking about buoyancy. Buoyancy is what, of course, keeps a boat afloat. It also, or a balloon up in the atmosphere. And of course, it's the same forces also that act on parcels of air and cause motions in the atmosphere. The main point of this slide, and I'm not going to go through all the little mathematical formulas, is that if the density of an object or a region, say inside of a balloon, is lower than the density of the air surrounding it, then there's a net upward force because the pressure below the balloon is due to the weight of the atmosphere all the way down to that point, but the pressure beneath the balloon is a little bit less than that because we didn't have the weight, the full weight of the atmosphere from the column that's in the balloon. So there's more upward force on the balloon than downward force, and the balloon will go up. And the same would be true of a parcel of air. And that's what we're saying here. Hot air rises. And once again, we're looking on the right is a theoretical cube full of air. It has a slightly higher pressure below it than above it. The difference in normal circumstances is that the increase in pressure over through that volume is due to the weight of the air in that volume. But if you solve the ideal gas law for density, N over V equals P over KT, you see that if the temperature increases, since it's in the denominator on that term, the density will decrease. So warmer air is less dense. Less dense air then would not provide the equivalent amount of weight as to the air surrounding the cube that's not warm, and so the cube would tend to rise. Because the atmosphere tends to decrease in temperature the higher you go, if a warm air particle goes up, it experiences even more dense, colder air, and so the force that tends to make it go up increases. And so a warm particle of air in the troposphere, where the temperature is falling off, is forced to go up and up and up and up. This process is called convection, and it's one of the main drivers for atmospheric motion on the Earth. Here's another example of a picture of the temperature profile. You see the lowest part of the atmosphere, the troposphere, is where the temperature falls off with altitude. Above about, on this chart it shows 15 kilometers or so, you have the ozone layer. The ozone absorbs some ultraviolet light from the sun and provides heating directly into the atmosphere, which warms it up, so the temperature stops falling off and starts to increase. By the time you get about to 50 kilometers, the ozone layer is no longer there. There's no absorption of sunlight in that, above that, and so in the mesosphere it starts to cool off again. And when you get into the thermosphere, the upper atmosphere, there's all manner of energetic sources in addition to just solar heating. There are the solar wind, there are charged particles, ions of various sorts whose motion is constrained by the magnetic field of the Earth, in addition to the regular dynamics due to the collisions of the particles. And there's heating due to other processes. In these lectures, we're going to talk predominantly about the troposphere and the stratosphere, and say hardly anything about the mesosphere or above. Okay, one other thing that we wanted to talk about that happens, that affects the motion of Earth is the Coriolis effect. On the left-hand side, you see an example of a Coriolis effect on a two-dimensional plane. This merry-go-round is spinning, and if one rolls a ball from the edge toward the middle, when the ball starts off initially, it's got, in addition to the motion you impart toward the center of the disk, the rotational component of energy from the outside edge. But as it moves closer to the center, it's no longer closer to the middle of the disk, the sideways motion is not as great. It's moving slower, but the ball is still going with the speed it picked up at the edge, and so the ball tends to outstrip the motion of the disk, and so it curves to the right. Similarly enough, the top guy is rolling the ball away from the center toward the edge, but in this case, the ball doesn't have very much of a sideways motion to the left because it's near the center, there's not much edge, and as it rolls farther, the disk the ball is rolling on outruns the ball, and so the ball still tends to curve to the right. So on the Earth, the three-dimensional analog of this disk, we have the same effect. In the northern hemisphere, the motion
if you're standing at the North Pole, the motion appears to be counterclockwise. Objects rolled, or for that matter, shot through the air in the northern hemisphere tend to apparently curve to the right because of the Coriolis effect. The objects in the southern hemisphere, because the motion there appears to be clockwise, objects launched in the southern hemisphere tend to curve left. The upshot is that along the equator, where you have rising air because of heating from the sun, air from the south and air from the south moving toward the equator, and air from the north moving toward the equator is deflected in a westerly direction. So around the equator, there's pretty much a permanent wind that blows in the direction of the west because of the Coriolis effect. These winds are called the trade winds, and they were used by sailing ships in previous centuries to enhance the ability to sail across from Europe to North America. Making the return trip, it would be smart to go further north, where the trade wind is not the pronounced effect, and indeed because of rotational motions, you can find regions where the wind is more favorably toward the east. Okay, there's a bigger picture of atmospheric circulation showing sort of the general trends. You see on this chart the idea, the white arrows indicating the general motion of the trade winds. You also see on the right-hand side in the northern hemisphere these circling patterns. Generally speaking, you get ascent near the equator and descent at the pole, but rather than being a purely straight rotation all the way northward in the higher atmosphere and southward in the lower atmosphere, the atmosphere does break up into these cells, which are maybe about 30 degrees in distance. And I'm not going to address the cause or the motion of these cells. I just want to make the audience aware of the fact that the so-called Hadley cell and the mid-latitude cell and the polar cell exist, that the motion of the Earth is the air is kind of broken up into three approximately 30-degree wide cells. And of course, superimposed on top of these general circulations is the wind. And of course, that is the topic of meteorology, and we're not going to discuss that at all in these lectures. So that's the last slide. So what have we learned? Hopefully we've learned a more formal understanding of pressure, temperature, and density. We've learned how these characteristics change with altitude in the atmosphere. We said something about the size of the atmosphere. We've talked about the gases, liquids, and solids that make up the atmosphere. We've discussed the names of the atmospheric layers. We pointed out that heat from the sun heating the Earth drives convection, and that is the principal driver of atmospheric motion, and that the rotation of the Earth through the Coriolis force influences the atmospheric motion as well. Next time we're going to talk about the chemistry of the atmosphere. We're going to begin with a discussion of spectroscopy, which is how we can detect and measure chemicals in the atmosphere. Every chemical has a signature in the patterns of light that it absorbs and or emits, and by breaking up light into its various colors and looking at the way the atmosphere, gases in the atmosphere absorb that light, we can tell something about what gases are present and in what amounts. Obviously, there are some chemicals released into the atmosphere that are bad, or they react to form bad chemicals. This is air pollution, and we're going to talk a little. We have some pictures of some really badly polluted air from back in the mid-20th century. and you can show you how bad it has been. And we're also, I guess, going to talk a little bit about the fact that the Environmental Protection Agency has been successful in reducing air pollution in the major cities. We're also going to talk about the chemistry of the stratosphere. The stratosphere is formed by the ozone layer, and the ozone layer is formed by chemistry up there. And we're going to go into some detail about that process of formation, and also talk about why it was possible that the chlorofluorocarbons were a threat to destroying the ozone layer and the consequences that would have on life on Earth. And I'm just going to make a point out that the fact that in general, the regulation of the chemistry of the atmosphere by the Environmental Protection Agency and the other agencies around the world has had a positive effect on the ozone layer and on pollution. So, hope to see you next time.